All right, well, thank you. Welcome back. I just want to make a couple quick announcements before introducing our panel, our moderator. Something I forgot to mention today. Just remember, after lunch today at 2 o'clock, we have the breakout sessions. These should be really great sessions, you know, pretty much expanding on all the topics we discussed during the conference. So just have a great brainstorming session about these topics and pretty much discuss if we can advance them at all. If there are any outcomes from this conference, if we can make recommendations so we can start advancing all these various topics we've talked about during the conference. So there will be a STEM panel in here, and we have a number of science teachers coming specifically for the STEM panel in this room. The science and technology workshop that Lisa May is going to be running will be downstairs. And the policy and advocacy breakout session that Lynn Billings will be upstairs. So I hope you'll all stick around for that, participate in it. I think it's going to be these will be really interesting discussions. So please stick around. And then at the end of that, at 4 o'clock, we hope everybody will come back and we're just going to give quick summaries of what we discussed during those sessions. So hopefully you'll stick around for that. I think it'll be quite interesting. At any rate, so the science panel, I've been really looking forward to this, particularly since you may have heard there's a Mars mission launching in a few weeks, and that hopefully will be quite interesting. I think it's perfectly timed politically as well, so I mean, it could really make quite an impact in the whole political season with a dramatic Mars mission in the middle of the presidential election campaign. So really looking forward to that. And moderating this panel, we have Mark Kaufman from the Washington Post. Mark writes about NASA and space issues with the Post. He's also been a reporter on the national staff for 10 years, being a foreign correspondent for the Post, reporting from Afghanistan after 9/11. He's also been the New Delhi bureau chief for the Philadelphia Inquirer. His articles appeared in many newspapers and magazines, including the Post, the Philadelphia Inquirer, New York magazines. He also has a new book out. This one right here, it's called First Contact, Scientific Breakthroughs in the Hunt for Life Beyond Earth. Just came out, published by Simon & Schuster, and he will be signing copies of this out in the front lobby just right after right after Rebecca Kaiser finishes her presentation. So I hope you'll go out, purchase a copy, and get a signed copy from Mark. I should say one more thing. You know, I want to end off with Mark's motto. Mark's motto is, time is short, use it well. So, ladies and gentlemen, Mark Kaufman.
Thank you, folks. Thank you, Chris. It really is a great pleasure for me to be here. One, to be surrounded by so many talented people, and second, it gives me an opportunity to kind of turn on its head a little bit some of the things that were being discussed yesterday. And I will be introducing the panel soon, but I just wanted to get this on the table. There are a lot of folks who are talking about how for women in science and in these fields that it's a very tough go. And sometimes it's difficult finding mentors and people who are going to be helpful along the way. I just want to say from my own experience, as a man, ironically in this context, it was just the opposite. In writing my book, many of my best mentors and sources and scientists were women, including two on the panel here, Pan and Penny, two in the audience, Pascal and Linda, the book was inspired by Sarah Seeger. So this is just my way of saying that although things may not have gone as quickly and as far as many women would like, it is a fact that there are now many women in important positions doing terrific work, and I have found all of them to be extraordinarily helpful and very affable. So with that said, to my mind, we have by far the coolest panel because we get to talk about the kind of wonder and awe that I believe should drive NASA and space generally. And this is where there are concrete things being done, where terrific scientists are doing superb work and finding things that just will boggle the mind, and that's what we will be getting into. First off, we have Lisa May, who is Program Executive of the Mars Exploration Program at NASA. She's the executive at headquarters for the MAVEN mission, which flies in 2013, and for Mars Sample Return. She also leads the Mars Sample Return Joint Engineering Working Group with the European Space Agency. And each of the women will also talk some about themselves and how they got to where they're going, so I will leave it at that. Deborah Bass is the Joint Mars Rover Science System Engineer for the, I got lost here, Deborah. What is it?
For the 2018.
Oh, I'm sorry. For the 2018 that everyone was talking about before. She also had worked as at a high-level deputy project scientist for the Phoenix project, and has a great deal of experience both in hands-on work as a geologist and also in organizations and involving communication. And next we have Pan Conrad. And Pan, I had the great pleasure of spending some time with. We went out to scenic Death Valley, among other places. And if you could put the slide on, or this is Pam in Death Valley, and both she and Penny are real field scientists as well as other things. Pan is one of the co-investigators with the SAM instrument on MSL and is deeply involved in all aspects of the MSL program. She's at Goddard right now, used to be at JPL. This was kind of hilarious because we were here on a salt flat, and that's a spectrometer or
That one's just a little thermometer measuring the temperature of the.
Well, in any case, there were a lot of people. As it got warmer, there were a lot of people walking, tourists, kind of walking here, and they would look at Pan and they'd say, and they'd come up to me and they'd say, "What's she doing?" And I said, "Well, this is astrobiology. You know, we're finding out about life beyond Earth." And they said, "Oh, yeah, right, okay." It was California. And Penny Boston, who you've already heard from, is a world-class speleologist and associate director of the National Cave and Karst Research Institute. I went to visit her in Socorro, and this is her office. It was really kind of overwhelming, and this is just a very small part of it. But I wanted to communicate this, as well as the great time I had in Death Valley and the Mojave with Pan, to say that many of the women scientists that I dealt with, almost all of them, were just really a lot of fun. And this is not like we're going to just work ourselves to death. This is fun. Okay, next slide, please. But just so that you don't think that it's just stuffed animals, for Penny, she also, as you know, spends a lot of time in very difficult places. This was for National Geographic. They had the masks on because of the sulfide, and she goes down very deep places. So, and this is extremely important in the world of extremophiles and analogs for life beyond Earth. So, with that, I will ask each woman to speak a little bit about how they got to where they are, and then I'm going to tee up a couple of slides just to talk a little bit about Mars history and Mars science, and then I'm going to be posing questions to these extraordinarily well-informed people, and we're going to get a great conversation going.
Something practical. I have no text there because I have no text.
Aha.
Because it's easier for our viewers, because there also is an internet. So. Sorry, I didn't have
Yay!
it. Now I do.
I forgot what it was anyway.
Yep, you got it.
Okay, we're all set now.
Lisa?
I feel so official. And now that I have a name, I can talk about myself. The beginning of wisdom is the use some proper names. I actually am on the science panel, but I'm representing an underserved minority in this group, which is engineers. And so but I'm a science enabler. That's my official job for the government, is to be a science enabler. And I came to this position in a really circuitous way. You'd think growing up in Florida, just south of the Cape, that I would have always dreamed, as so many have said over the past 2 days, of being an astronaut, being in the space program, and nothing could be farther than the truth. I was not completely uninterested, but I wasn't aware of the influence until I ended up at NASA. I was just young enough that when I was really good at math and science, the counselor didn't tell me to become a nurse. She did tell me to become a doctor. And nobody told me what an engineer or a scientist was. And I had no clue, and I went to the University of Virginia and found out I would be a really lousy doctor. I was not enamored of the pre-med program in any way, and so I cast about and got an undergraduate degree in speech communications and worked in radio, which was an obvious trajectory. But from there, I was not particularly satisfied with my career prospects in radio. And I wanted to get a master's degree in something, and because of some personal connections with professors in the engineering school and the guys who lived in the apartment downstairs who were in engineering school, and I figured out what an engineer does, I ended up getting a master's degree in mechanical engineering. And it stuck, and we had a conversation last night, some of us, it felt like coming home. For me, writing 20-page papers about the ethics of rhetoric in Washington's final farewell address was seriously hard work, although I do pride myself in being a pretty good writer. But when I got into engineering school, it was so clear and so obvious that I was home. And that is where I should have been all along. But in retrospect, I'm very grateful I wasn't, because I find the communication skills are never wasted, and it was a worthwhile thing to have done. And over my career, I've done a number of things, most of them in and around NASA, and I've been a NASA civil servant for 9 years after having had my own company. And when I moved through NASA jobs and ended up in Mars, that too was like coming home. Mars engineering is where I really belong. And so to anybody who is young, listening, watching, or here, if you're not sure where you're going with this, and you're not approaching 45 or 50, don't worry. It takes some of us a while to find out where home is, but there are a lot of homes in science and engineering at Mars and in NASA and in other fields.
I have to say I resonate with a lot of what Lisa said, but I just wanted to start out, which is that I just arrived last evening to this conference, and so this morning's panel was the first one that I saw, and when I saw all the rows of suits lined up and the formal written prepared items, I thought, oh dear, I'm really ill-prepared for this, given that I wore a dress, and that I didn't actually prepare any remarks. But I'm feeling much better now, thank you. I guess I want to say that I started out loving science fiction, but I thought that to work in space, you needed to be an astronomer. And I don't like gas or balls of gas. So that wasn't really going to work for me. My family is all in the medical field. My aunts, uncles, sister, father, mother, etc., all work in some form of medicine. That was what I was supposed to do as well. PhD was piled high and deeper. So when I decided that I was actually going to become a geologist, I didn't tell my parents. And in fact, I didn't declare my major in college until my senior year because I didn't want them to worry or get upset or have problems. And I took all my pre-med courses. But I didn't know what I was going to do with this geology degree until I found out about the field of planetary geology. And I thought, holy smokes, I can marry my love of rocks and my love of this hard stuff and the notion of a system with my love of space. And boy, wasn't that terrific. So from there, I thought, well, I really, if my real desire was to study life outside of the Earth. But when I was getting my degree, this was something kind of that you did on nights and weekends, and it was very difficult to get funding for that. So I went into Mars water instead. And I have sort of come back around now to the search for life from this Mars-water life connection. And it has been fabulous. I also learned that one of my strengths is managing people and working between different organizations, different groups. So I work as a science system engineer. I'm a pure trained scientist, and I learned about what engineering was. I learned about the notion of a requirement, which if you don't know, it's okay, but
No, it's
but
not okay.
engineers deal with requirements. And so I learned how to talk to both scientists and engineers. And it's been an absolutely fabulous place for me to work sort of in all of these different areas and try to bring them together to facilitate science. So I'm working on the 2018 Joint Mars Rover mission, which is the first of the 4-step campaign for Mars sample return, as a science system engineer on that project. But I also manage a group of science system engineers at NASA's Jet Propulsion Laboratory who do this communicating between scientists and engineers for a whole range of missions: Dawn, Juno, Mars Science Laboratory, Mars exploration rovers, so on and so forth. So it's been a great place that I've landed, and I never thought I'd get here just from loving science fiction.
Wow, that's an interesting story. First of all, I would like to thank the engineers, because those of us whose experiments are sitting on top of a rocket on pad 41 getting ready to go couldn't do that without the engineers, so thank you for enabling. So I came to science through a very atypical route. I do have a very early memory of loving space. My father took me outside when I was preschool, and we looked up and we saw Sputnik. And later, when he made one of those Revell plastic models of the Explorer with launch vehicle, I took it and went all around the living room flying my rocket. So it's been a very important part of my childhood. However, I didn't follow that educationally. I will say that I became an astrobiologist very early. When I was 13, I did science projects that actually turned out to be astrobiology, although I didn't know it for another 40 years. And I have something that I always take with me when I go on an expedition, or if I go to do something really hard, like get a colonoscopy, and that is, it's a medal that I won from NASA when I was 14, and it was put in my hand by the NASA administrator. And I haul this out often when I give a talk to remind you all that if you think EPO doesn't matter, it does, because here I am. So I went to college. I was a hippie. I majored in music. I had every intention of going on to theological seminary and getting a degree in sacred music. I knew it would really piss off my parents, so I didn't. I went to Texas and I got married instead. I came back. Back is actually here. All of my degrees are from GW. I got another degree in music because one isn't enough. And moved to New York. And the scariest thing I ever did was stand in front of a panel of 4 people who weren't smiling and audition for the Metropolitan Opera. I didn't get picked. I did get to be an apprentice, though, so that was pretty cool. Later on, I decided that I would do science. Between careers in music and later in video and other types of media production, one day I was doing a gig here in DC, and I cut through Bell Hall, which used to be the location of the now defunct geology department here, and I looked at all those crystals in the showcase. I was 36, and I said, okay, that's it. I'm going to be a geologist now. I applied to school, and they laughed. They said, well, you have an exemplary academic record, but you really need to have some science if you want to study science. And I said, okay, well, I'll make some of the courses up. So I talked them into letting me take a couple of classes and a couple of exams, and finally I got admitted into a program in geobiology. And that was novel, but the geobiology program here actually was people studying human origins and paleontology. I said, no, I want to study the contemporary relationship between organisms and rocks. And they said, well, no, you can't do that. And I said, okay, well, I'll just be a geologist. So I did mineral physics. And I did some work at the Carnegie Institution of Washington, all of my research. And when I left there, I got my first job, which was at Jet Propulsion Laboratory as an astrobiologist. How I talked my way into that, I'm still unclear. I think it was because the man who hired me was in town for a meeting here, and I went to see him dressed up in my bicycle gear because I was getting ready to go out on a ride, and I guess he figured I was informal enough to fit in with his California group, and so I did. I'm going to cut to the chase quickly because we shouldn't spend too much time on this, but I want to say something that has nothing to do with my personal history more than anyone else's personal history, and that is the reason you become a scientist. The most important part is because of nature. And I looked up in the sky, and not only did I see a piece of technology circling the Earth, I saw all the stars, I saw the moon, I saw the planets, and I looked down and I loved the rocks and I loved the frogs and the tadpoles and everything else. The reason I'm a scientist is because of nature. The reason why we're all scientists is because of nature. And the reason why engineers help us solve problems to explore new places is because of nature. We all explore. It's a biological imperative. Adventure seeking is something that humans kind of tend to do. But exploration is something that every organism does, and we share that in common with microbes. We need to explore. So as we go into the topics we're going to explore here today, try to bear in mind when you ask those questions, how did you get here and what do you do to maintain that? It's just explore. That's it.
Cool. That's amazing, Pam. I'm glad you told that story. I'm glad I'm on this panel so I can hear it. Well, I come from a theatrical family, and went on the stage myself at 4, and went on the modeling runway right after. So if it hadn't been for really the input of science into my life through school, I had no family history of that, I guess I would have gone into a performing art. I love performing arts. I still dance and write poetry and so forth. But I was captured by science at an early age, and really a lot of it was science fiction, like Deborah. And I wanted to get on a spaceship and go cruise the galaxy looking for weird things with lots of tentacles. Right? I'm one of those people, and I think many of us are, that E.O. Wilson calls a biophiliac. Right? And in fact, he has talked about the fact that our whole species is biophilic, that we are life, we're conscious of being life, and we seek life, and we love life from the very core of our being because it is life, okay? So that sensibility, I guess, really informs all of my science, but that doesn't mean that I wasn't in love with every other kind of science. I was. So I was a real science geeky kid, but because we were theatrical people, we moved around all the time. I was in school infrequently. I was tutored a lot. And so I never got any negative feedback for that, because when you come from an external community of nomads, you sort of don't care what the townies think of you, I think, you know what I mean? So we were always the perpetual outsiders. And so I just was sort of self-defined cool, you know. So I never got any negative feedback for being a really science-oriented kid. And I carried that with me. That was always my intention. And I think I mentioned yesterday that one of the ingredients in my formative life was a copy of My Weekly Reader with the Drake equation and reading about Frank Drake, who many years later, of course, I've come to know him and appreciate him as a person. But then it was this shining idea that you could actually calculate something about something you couldn't actually know about. So for me, that was an entree into what was then called exobiology, but it was also an entree into the wonders of math, why math would actually matter, because you could use it to think about stuff that you couldn't think about as effectively just by thinking about it. I went on to drop out of high school. I was also a hippie. And I don't like being told what to do. And so high school was certainly not for me, so I dropped out in the 10th grade. But Florida Atlantic University in Florida, which is where I grew up for part of my time when we were not in Europe, was the home of a program that allowed talented high school students to test out. So I went there, I took the test, they admitted me, and I went in as a junior. And it was a compressed 3-year program. Those of you who know Chris McKay, we were in the same cohort. We've known each other since we were 17. There are many other people whose names you would probably know who were in that same cohort. And so that was my undergraduate period of time, and I focused more and more on really what you would call exobiology, but at that point it was not a respectable major. You could not get a major in anything even close to that, right? So times have changed. So of course I majored in biology and minored in psychology and geology. And just about the time I was finishing my undergraduate career, Viking landed on Mars. And I was heading to Colorado from Florida because I decided I wanted to go there, and that's probably where I wanted to go to graduate school. And I was watching on the television as that first picture from Mars slowly rastered on the screen, torturous moment by moment. And it was a complete frame shift for my entire consciousness. I mean, I was interested in planets. I was interested in everything. I was interested in fish. I was interested in worms, you know. But when I saw that picture, it turned a dot in the sky into landscape. And that was the moment that really, focused always in the back of my mind, Mars, right? So I'm a fanatic, right, really, about it. So that led to one thing or another. I was a graduate student at Colorado. Chris McKay also wound up there, Carol Stoker. And at the time, this was the Reagan era. Reagan had just come into office, and there was a great turning away from the idea that we would explore planets. And this was very disturbing to those of us who were young and interested in planetary exploration. And so we decided to do something about it with the hubris of and naivete at some level of graduate students. And so we put together the first Case for Mars conference based on a Mars study project that we had put together. And really, it was very futurist. It was not the kinds of stuff that we all now do in our daily work. It wasn't missions and stuff like that. It was terraforming. It was, cutting to the chase. It was like informed by this issue of the capturing imaginative aspect was, how could you take another planet and make it like Earth? And in order to do that, you had to learn one heck of a lot about that planet. And you had to think more deeply about Earth than I would ever have done. So in terms of being heuristic, being instructive about the science that I now do, thinking about that almost science fiction concept probably has mattered to me more in my development than all of the formal down-to-earth stuff that I have done. Because it caused me to get out of myself and get my brain off my own planet and look at Earth as an astrobiological object, right? So that was very early on in my history. And I have worked on legitimate science. I always keep one or two fingers in the human life support issue. In fact, the first paper I ever published in 1981 was on growing plants in Mars-like conditions. And I've been a space advocate for human exploration. So there's the science part of me, but there's also the explorer part of me. And with the first conference that we started in 1981, I've organized a zillion conferences on related topics over the intervening 30 years, and I'm still going yak, yak, yak and talking about Mars. So that's my career. And hopefully I'll be doing this until I just finally, drop in my tracks. Thanks.
Well, thank you all. And as you folks can see, the paths to these kind of positions are not straight at all. In fact, that's the take-home message I got from astrobiology generally. This is both men and women, that almost nobody started out doing what they ended up doing, and almost all of them had huge obstacles to overcome in order to get to where they were, because people told them what they were doing was ridiculous. And then they persevered and proved to be in many ways correct. So that is again, one of the great lessons, I think, of all this. One other thing I would like to add before just showing a couple of slides is that I heard the discussion earlier about how the public is not terribly interested, or appears to not be interested in what NASA does or doesn't do. As a reporter, I write a lot of stories, and they're almost always about NASA science. In recent years, exploration has been kind of a bureaucratic mess, and it has not been that exciting. Science has been remarkable. And I can tell you, we now have metrics. We can see who is clicking on the stories, and they're huge. There's enormous interest. I mean, they become the most viewed stories of the day, and sometimes for several days. And it's not just me, it's the science. I kind of throw that out as a way of saying that while NASA exploration has got a lot of problems now, NASA science is kind of still in a golden era. I was just talking to Jim Green a couple of days ago, last week, and he was saying, this 50 years from now, people will look back at this as saying the golden era of planetary science. So with that, if we could have our first photo, which is appropriately Mars from Viking in '76. This is not that first image, but the first color image. And as you can see, it's a beautiful place. It's just for those of you who were not around then, the expectation, I think it would be fair to say, when Viking went, was that there was like a decent chance that they were going to find something that was biological. No one knew for sure, but that's what the goal of the mission was. It was an astrobiology mission. There were 2 landers, and they had a number of what, in retrospect, were quite rudimentary kind of tests. Okay, so this is what they found, and there was like no giraffes walking by. It was pretty clear that things were fairly bleak. There was the conclusion that NASA came to was that they did find nothing biological. That remains a somewhat contested view, because one of the researchers, Gil Levin, says that his biology labeled release experiment did in fact come in positive. I think the consensus is that there were extenuating circumstances. Okay, I hit a button. Okay. Just a kind of continuation on that. What sealed the decision was that there was another instrument that looked at whether or not there was organic material on Mars. And it came up negative. Now, if you don't have any organic material, you're not going to have biology. As I'll show a little bit later, that is, that test was probably, or almost certainly incorrect. But that back in 1976, 77, 78, kind of created a paradigm that said Mars was probably dead. May have always been dead. This is a relatively recent image put together by NASA. There is a growing consensus now that back in the day, 4 billion years ago, that Mars actually was kind of wet and warm, not the cold and dry that it is now. And as a result, it was potentially a far more habitable kind of place, although we may find that it is in fact habitable now. I don't know, deep down. And that has part of the revolution that that exploration and satellite imagery, and I'm sorry, the satellites that go around, that orbit Mars, have given us this kind of information and have, under the rubric of follow the water, have told us all kinds of amazing things. This is from Phoenix, a picture that Deborah, I'm sure, is familiar with. They found what very much appears to be water ice, just a couple centimeters down. This is part of a growing understanding that there is a lot of ice underneath the surface, and that all the water that was once maybe the oceans of Mars some of it flew away, some of it may still be there. And I think what the red arrows point to is that there's change occurring also, and there is, in that sense, melting. What Phoenix also found was the substance perchlorate, and analyzing the perchlorate and what it could do to the test back in Viking days for organics. Chris McKay, who we just heard about before, and his colleagues concluded that the perchlorate, the level of refinement on that instrument was not great enough, but two, that the perchlorate could change people's understanding of what was happening. We now know that there are all these water gullies and deltas and whatever on the surface of Mars. When you think about it, it's kind of amazing that we have, at this point, the kind of detail that we have, and perhaps most amazing. Whoop. Yes, this image. This was from Mars Reconnaissance Orbiter, and it was published in Science just a few months ago. You look at the black on the left. I mean, this appears to be some kind of running water. The way it was presented, that it was likely briny running water that melted when the sun hit this escarpment, and this, again, if it turns out to be correct, we don't really know yet, is something that will once again kind of revolutionize our understanding of a place very, very far away that was written off as dead. And finally, there was the finding about a year and a half ago of some localized heavy releases of methane. On Earth, 90% of methane is formed through biology. Doesn't mean that this was formed through biology, and there's been some controversy about the calculation, but there's always controversy about calculation. And I think it would be fair to say that the gas orbiter in 2016 was designed to some extent with this in mind. So there is a level of confidence that this is going to turn out to be correct. So if there is methane, there is a perhaps even greater chance that there is life. And final thing here, when we talk about exploration as being what NASA is about, I would add to it that I think from a public perspective, the search for life beyond Earth is kind of what it's all about. That going to places is very cool, learning things about them is very cool, landing people on the on the moon or asteroids is very cool. But if you find that there was life or is life somewhere else, that will be world historical in a different way. That will be Copernican. And that's, I believe, what the public kind of intuitively is most interested in. So with that, what I'm going to do, being a reporter, is start asking our esteemed panel some questions, and they will use their expertise to kind of address them. And we have a complicated system with the slides that may or may not work, where we're going to try to pull some things up as if people want them to be available as they talk. So let me sit down here. And I'm going to try to do this in both a generic, we're going to try to do it in both a generic way about the themes and then also some of the missions and some of the other research that's going on. Okay, so going back to follow the water, it's long been NASA's mantra for Mars. What is our state of knowledge about water on Mars now? And where is that storyline going?
Am I supposed to take that one?
I'll yield to a water geologist.
Whoever would like. I mean,
Water over your head.
Okay. Well, it's right here. No. So as you saw from the slides Mark showed, we went from thinking about following the water following the water was a theme to try to understand Mars. We were going to look at water in terms of geology, water in terms of climate, water in terms of potential for future human exploration, and the water-life connection. Now, I think, like I said, I wasn't here yesterday, and I don't know what all of your understanding is about the water-life connection, so let me just take a moment to sort of make that for you, which is that everywhere on Earth that we find water, we find life. So the fact is that you need a certain number of things to produce life. You have to have an energy source, food. You have to have water. You have to have the elements that create life: carbon, hydrogen, oxygen, nitrogen, little sulfur, little phosphorus. So if you have all those things, you have kind of the basics for life. But without that water, it's just, it appears, we believe that it's just not possible. So the reason we're so hyped on this water business on Mars is because of that water-life connection. And the fact is that it looks like on Mars there was water, liquid water, flowing on Mars about the same time that life was forming on Earth. And I think Penny may be able to speak some more to those kinds of things. So the likelihood that life might have originated on Mars is the probability is higher because of that water-life connection and the timing. Okay? So we started out with this whole follow the water business, trying to understand Mars as a basic planet, but really, as Mark pointed out, to follow as baby steps towards trying to get to the search for life question. And we feel that we have learned a fair amount about Mars, and that we've sort of moved beyond this following the water goal to looking for zones of habitability. Now, I love that word, habitability, say it 10 times fast. The notion being that we're now looking for places where life on Mars could have originated. Where are all of the ingredients together in a place where it could have been sheltered enough and maybe still is there? We don't know. So that's how the life on water question, I would say, has evolved.
And just taking off from there, when I was when Pan and I were out in Death Valley, she was preparing, as she said, as an Olympic athlete prepares for their events, she was preparing for the MSL, and her specialty is habitability. So, Pan, if you could play that out a little bit more in terms of what MSL is going to be looking for and what we know about habitability as kind of a part of this whole story.
Sure. It is hard to say habitability, so I can substitute livability when I'm trying to articulate this. The fact of the matter is we don't know a lot about it. There are a lot of assumptions about it. And sometimes they're simplistic assumptions, and that makes it tough, because unless you know where in parameter space you need to be to make an assessment that some place is potentially livable, you could miss key factors. So the approach that I take, and I'm going to tell you what I do, and then I'll talk a little bit about what we would do on another planet that has to, out of necessity, be different. I'm taking a very, very broad, multifactorial approach on Earth. We do agree pretty much that life on Earth has to have some water, and that's because of the key chemical characteristics of water and the multiplicity of roles it plays in biochemistry. It's essential to duplicate all those roles to make the molecules and engage in the commerce of metabolism. And without filling that role, you can't do that chemistry. Is it possible that some other chemical could do it? Possibly, but it makes very little sense to try to dream up a different scenario when we have one that works very well on Earth. Now, we have some intangibles. We always say that you must have an energy source to be habitable, but we don't get down and dirty the specifics of supplying that energy source. Its nature, how it is transduced from source to usable commodity, that's tricky. And we don't necessarily have a good answer for that, a good model. But there are other intangibles. My personal interest is in the physics of environments and what those physics forcing functions do to make an environment work or not work. For example, ionizing radiation is hellish if you can't repair the damage it does quickly enough to keep going. On the other hand, ionizing radiation, let's just say, the decay of something that's radiogenic deep within the Earth is also a heat source and could be a heat source on Mars. There's a magic balance between things that could be deleterious and things that could be enabling. There are all kinds of factors like that. The right spectrum of solar energy is essential for photosynthesis. It has to be the right intensity and it has to be the right color in order to do that kind of photochemistry. Mechanical stability is important. You can't live on an alluvial fan very well, but you sure can live on the edges where the water collects. It's just too mechanically unstable. Now, here's where Mars comes into play. Mars is key for a number of reasons, and we don't have to justify it here because we're all here because we love Mars. But the most important thing that motivates me to study Mars is this. We got made at the same time 4.6 billion years ago. Somewhere between 4.6 billion years ago and now, we've become robust, but it doesn't mean there weren't obstacles to be overcome. There was a huge obstacle to be overcome throughout the inner solar system, somewhere between 4.1 and 3.9 billion years ago. We call it the late heavy bombardment, where huge protoplanets crashed through the inner solar system. We don't have a lot of evidence of that on Earth because we are still so tectonically active. We've subducted all of our evidence of that time period. The oldest things we have are about 3.8 billion years. But on Mars, that stuff is still there. That's a good news, bad news story. What happened was some giant impact really messed up the planet badly. It lost its, I was going to say geodynamo, but I guess it would be its Mars dynamo. Anyway, the active movement inside the planet, which creates a magnetic field which helps protect a planet from the deleterious effects of ionizing radiation, either background galactic cosmic rays or solar energetic particles. Magnetic field went away. Bad news, the atmosphere went away too, most of it. And we think that one good model that we have for that is that the solar wind basically ripped the atmosphere from around the planet, leaving this very thin carbon dioxide atmosphere. Now, the reason why that timing and why I'm giving you this whole song and dance about this is because if Earth and Mars were made together and they started out similarly, denser atmosphere at Mars, a bigger array of chemical elements, a Mars dynamo method of retaining and producing heat, Mars could very easily have produced life. Mars could very easily have evolved the complex chemistry that is necessary to be a habitable environment. And that information is still on Mars. So how we get to that information is what we're here to discuss. Do we go there? Do we send people there? Do we send robots? Do we bring back samples? So the answer to those questions is yes, all of it. And the biggest part of it is we have to look at a lot of planet. Viking did the best it could, but it could only see a couple of samples. MSL is going to look at tons of samples. My experiment, Sample Analysis at Mars, which is a suite of 3 spectrometers, is designed to not only sniff the atmosphere and look for volatile species, but to evolve gases from solid samples and then sniff those gases that come out. If there is an organic molecule to be found at possibly subparts per billion level, we're going to see it when we ingest the sample. If there's methane in the air, or in fact any other organic molecule in the air, we can see that at parts per trillion level with the tunable laser spectrometer that's part of SAM. So what I'm going to tell you is this. We can see organic molecules if they're there at the limit of detection of our instrument, which is very sensitive. We can go to a lot of places, but we can't go to the whole planet. You can't do that with one mission. We're landing in a crater. It's just south of the equator on Mars. We'll be able to look at a lot of stuff. We've got 74 sample cups. We could look at 10 samples per cup. We could look at 740 samples. But really, you know, given the whole suite of instruments that's on Mars Science Laboratory, we have to share, we have to get context information, we have to learn mineralogy, we have to learn the radiation environment. So there's going to be a lot of experiments, and we're all going to work together in the 2 Earth-year nominal mission. So that tells you a little bit about how we'll do habitability, and then I'll shut up, but I want to get back to the thing I promised I'd tell you, how we do it differently on Mars from how we do it on Earth. On Earth, we go to a number of different environments. We set the stage by saying we're going to explore X amount of space, spatial space. And then we look at the numerous pieces of parameter space. I make over 15, 20 measurements when I go to measure an environment. And then I do a biological inventory. I use molecular probes. First, to determine the diversity and abundance of biology in the space I'm measuring, and then to determine the viability of it. I measure everything, the slope, the mechanical stability, the amount of water, the redox potential in a spatially distributed way, the difference in gases just close to the surface from, say, 2 or 3 meters above the surface, the incoming solar radiation at different hours of the day, all kinds of things, mineralogy, chemistry, magnetic fields, electric fields, everything, because we don't know what makes a habitable environment. And by making all the measurements and correlating it with the life that we have, we can begin to develop a predictive tool, something that uses empirical data to tell us where we might have a livable environment. And that is the next generation of the Drake equation. Something with enough parameters constrained that we can predict environmental types, turn it over to our exoplanet friends, and then try to adjust those numbers to propagate the number of potentially habitable worlds.
Remarkable and exciting stuff. I want to ask Penny some questions about extremophiles, but first let me ask Lisa something. This is what's happening now with MSL and then MAVEN, which I know you're a part of, hopefully you could tell us some of what that's about, is part of an ongoing program. Could you tell us about that? I mean, you know, to the public it seems like, well, there's this and this and this, but I know there's a lot of planning.
Yeah, and actually, if I can get, there's slides that were either affiliated with me or they say LDM, I'm not sure what you're using to cue. I'm only going to show one of them, so. Well, I'll just start talking. So it's the second slide in the LISA charts or the LDM charts, if you have those, please. And it's a build out, so I'm going to need you to stick with me. Next one. So this is a roadmap of Mars exploration in the recent past and where our current plans say we're going to go in the future. And as Deborah pointed out, let me start with something very basic. We listen at NASA headquarters, what do we do? What's our job? We listen to the science community. We listen to the experts who understand what the big science questions are, what the big science goals are, and help us prioritize what we need to do in order to understand those things and answer those questions. And from there, we formulate missions that go get that data. And as a systems engineer, which seems to be a common thread among several of us on this panel, my comment has always been no one actually cares if you use passenger pigeons to get the data as long as you get the data. And so these implementations, these embodiments of Mars science, some of which we know and love as the rovers, is really the means. It's a set of tools, an increasingly sophisticated set of tools that NASA puts together in order to enable those measurements that then get analyzed and from which we draw some of the amazing conclusions we've drawn and understand the questions we're still looking to answer. And it is, at Mars, unique because it's a coherent program. It's our nearest neighbor. We can go every 26 months, which turns out to be a pretty good cadence, both budgetarily as well as chronologically in terms of developing missions. And so it's a good target in a pragmatic sense. As Pan said, it's a good target because there's a history still there. They don't have, I mean, Mars doesn't have, I always say they, as if there are somebody living there.
What do you know that we
can't
don't
help
know?
myself. I've tried to break myself of it for 6 years now, and I guess I'll just keep doing it. So the whole system at Mars, we've come up with a path that's community-driven and peer-reviewed and competitively selected science to go and get at these questions. And we launched earlier in this century, we launched Odyssey and MRO, and our ESA compatriots launched Mars Express, and they have been doing amazing orbital science. And this gets at what Pan was talking about in terms of we can only put landers and rovers in one place. When Pan's MSL instruments sit and look for methane, it will be in the place where the rover is. The rover may not be in the place where methane is if it's there. And we may have more than one place. And so we send orbiters to get the global view, to understand the planet as a whole, to help target our more in-depth surface missions, and to help us do basic science. The paper that just came out the other day about, well, perhaps the water was always subsurface as opposed to at the surface, although it's clearly evident there was persistent liquid water somewhere on the planet in order to form all the minerals we found. So could you hit one for me? So MRO and Odyssey really have contributed to the global study of Mars history and geology, the mineralogy that we see with the instruments, as well as the history of water, not only in the mineralogy of the rocks, which tells us that they were formed in the presence of water, but the features like Mark showed, which are gullies and which appear to be seasonal flows of something that could be explained best as we know it right now as briny water. Next. One more. We had Spirit and Opportunity, the rovers, which were launched in 2003, landed in 2004. And one of the things that post-Viking, Viking went, and Viking looked at one place because it was a lander. And as soon as we landed the rovers and realized there were outcrops that could give us a history of stratigraphic record there, and we saw blueberries, these little inclusions in the rocks, a rover is an obvious thing to do. It gives you some mobility so that when there's a beautiful target there, you can go and look at it and study it and use your rock abrasion tool and conduct experiments. And so Spirit and Opportunity have given us a tremendous understanding of well, an increased, far greater swath of Mars than we ever expected them to. Next. Phoenix, which landed in 2008, and Mark showed the images that showed evidence for the presence of water, ice. It saw snow at the North Pole of Mars. Next. And we have MSL launching in a few days, and landing August 5th or 6th, depending on your time zone and part of the world you live in, next year. One of the interesting things about trajectory design and mission design and science enabling is we actually know when it's going to land. It doesn't matter when it launches, it's landing that day. And it will be an amazing feat, as was shown yesterday. The landing system that Colleen showed will be first of a kind and enabling forward for landing larger and larger systems on Mars. And the point I want to make about the rovers and future missions is that you're kind of like going on a trip. And you got your carry-on luggage, and you're going somewhere where you can't buy things. You're going to an island. And so when you get there, you do what you do, and you do it where you do it to the extent of your ability to travel. But you can't do something different. You can't go and buy something at the store. If you took beans with you on your expedition, you can't go buy hot dogs to go with them because all you have are beans. And that's it. You have your carry-on luggage when you go to a planet and do in situ science. It's the carry-on. And you haven't got a credit card or a store to go to. And so while we are doing increasingly sophisticated search for organics and understanding mineralogy in places that are better and better understood through the use of the orbiters, the reason the decadal survey prioritized the beginnings of Mars sample return in this decade and investments to enable it in the next decade or beyond is because really, if you're looking for something like life or history of life or very sophisticated things that may contain surprises, you want to bring them back. You want to look at that sample and you want to say, wow, I never thought I'd see that, and be able to say, here, you come look at this, and bring all of your instruments and all of the things that I don't have in my lab or that I couldn't have put in the carry-on luggage that I took to the surface. And that's really the gist of it, is we'll never bring back, I mean, we'll still send a rover, and the rover will go to a specific place, and a rover will collect a specific suite of samples. But the ability to have discovery and follow up on that discovery with different tools and different people. I'm sure many of you, being Marsophiles, know about the Allen Hills meteorite, in which, was declared that there was evidence of life in that, fossil life in that. However, of course, it was immediately contradicted, and to this day it's still controversial. There's still papers being published on it. But if we go and we do in situ science and somebody makes the equivalent claim about something they've seen on Mars, until we bring something back here, that scientific debate, which is my job to enable, won't occur. It will be what it is. It will be the Viking result. It will be, perhaps we'll go later and see perchlorate and make some other conclusions about what we see. But that analysis and different methods and different tools is really the motivation. And it's a coherent program of looking for, are we alone? How did our planet form? How did the rest of the planets form? And going through this coherent program, we're going to hit the next one with MAVEN, and I'll talk when Mark asks me about MAVEN, because I could talk a long time about that. That's one of the missions in my portfolio. And the trace gas orbiter, which again can give us that global perspective atmospheric composition. So that's it. Thanks.
Okay, thank you. One of the really wild worlds of astrobiology and planetary science now is extremophiles. These are microbes, and we now know beyond microbes, roundworms also, that live in conditions that 10, 15, 20 years ago were thought to be utterly impossible. Of course, for these extremophiles, where we are is extreme, and they're living where they should be living. But this is the kind of world that that Penny is very much involved in, and be interesting to hear you talk about how your work in caves and in looking at extremophile worlds here, how that is significant for Mars exploration in terms of analogs and so on.
Well, I'm certainly not the only person playing the extremophile game. There's a long history of this. And one of the early efforts to do that, of course, was at Yellowstone, where people noticed visually that spectacular colored organisms were growing in boiling or near boiling conditions. And so that was focused on in the mid to late 60s by Tom Brock and his students. Within a decade after that, we had discovered the deep sea hydrothermal vents with organisms making their living at very high, apparently very high temperatures, and without the benefit of sunlight, or certainly without the immediate influence of the above ground biosphere. And gradually over that intervening 40 years, really, the discoveries have come thicker and faster. And this has always been what has attracted me, because I work on the cusp of life. So I'm interested in what life does to the non-living part of its environment. So that we share that interest, Pan and I. In my case, I'm looking for biosignatures that are typically biominerals, right? And I'm looking mostly at organisms that make their living, or the ones that I focus on the most, are the ones that make their living not off yummy organics, but off oxidation of metals and minerals. And they get that little tiny quantum of energy from that reaction, and that's what they use to drive their life processes. And so in the early 90s, I published a paper, which is certainly the most cited paper I have in my career, with Chris McKay and Misha Ivanov from Russia, suggesting that the last best place to look for life on Mars would be in the subsurface. And at that point, I had never been in a cave other than as a tourist, a few times as a kid. But drilling is expensive and difficult. And so we were looking for an alternative to trying to study what seemed to be emerging 20 years ago as an undiscovered, rich microbial biosphere in Earth's subsurface, which was completely new. In the late 80s and early 90s, this was coming to light. And so one of our other colleagues, Larry Lemke, who is still at NASA Ames, had seen a National Geographic special on Lechuguilla Cave in New Mexico, which at the time was newly opened. And what Larry heard in that National Geographic special, which I had not seen at that point, was it was a very deep cave. It was pristine because it had no natural opening. It had to be dug into, and it was covered in sulfur compounds, sulfur minerals, and Mars is a sulfur-rich planet. And a fellow from USGS named Kim Cunningham had seen in petrographic slides of some of the formations that he was looking at in that cave what he thought were microbial forms. So we were instantly hooked. So I call up this Kim guy, because he was in Denver and I was in Boulder, and I said, "Hi, you don't know me, but we're from NASA and we like to go in your cave." And so that was in the early 90s, and that was my first caving trip, and it nearly killed me. Lechuguilla Cave is the deepest cave in North America. It is a massive grunt fest of exhaustion and with skills that we simply didn't have. We had 3 hours of training on a cliff face outside of Boulder, learning how to put the vertical gear on, and then we jumped off the cliff and we said, "Okay, we're ready." And then we did, a 6-day expedition underground. It was really insane. And so the whole time I was in there, I thought, well, I just have to live long enough to get out. And I got, a big pile of this fluffy material from the ceiling that I just looked at, and I said, that looks like soil-forming processes, except for, from looking underneath. All right, this was an intuition that I had, and this blob of stuff fell in my eye, and I got a massive eye infection. I thought, bingo, it's gotta be life or something, And so I had to make it out of the cave with no caving skills, up 180-foot, cliffs that we had rappelled down where gravity's your friend, but it's not your friend going back up, with a busted rib and a taped hand. Which is still never healed. Okay, this is my souvenir of my first trip to Lechuguilla. And we got out, and I thought, well, phew, I dodged, death once again in my life, and I was covered with bruises like a pizza, and I thought, oh, good, that's all, we're done. And but we are wonderful creatures with very short attention spans to pain, and this is undoubtedly one of our great assets as a species. This is why we all, have more than one child. Some of us. I have one. But the bruises faded, and I realized that I had been in a place that was unlike any place I had ever seen. That's what stayed with me. It's a magnificent cave. It is rife with unusual mineralogy, and I just smelled there was biology in there. And every part of that cave was different. It wasn't like a little limestone tourist cave. This cave has been created by sulfuric acid millions of years ago. It's had a long and complicated history with iron and manganese. And so it had Mars-likeness all over it, And so I learned to go into the subsurface safely. I learned to become a caver so that I could go into places like that. And I've been into many of them around the world with all sorts of different exotic environments. And the scientific payoff has been enormous because these are essentially unexplored terrains. And the fact that it's so damn difficult means that I have less competition than I would be if I were studying Yellowstone. So it's been a major refocus of my career away from surface extremophile environments. So that's the caving part of it. But all of us, no matter what extreme environment we are studying, are looking for the things that you were talking about, Pan, which is energy. And you were talking about energy is critical. The access to some kind of water, and sometimes that can be very subtle. A lot of the organisms we're studying can get by with incredibly tiny water activities. I have to tell you one anecdotal piece of information that we're trying to figure out how to write up and publish. We're studying copper organisms in a number of different subsurface environments. And these guys are a consortium of different kinds. This is a common thing that we find, that it's often very difficult to isolate single strains. That these guys are acting as little symphonies of biochemistry. And in this case, there are bacteria that are oxidizing the sulfide in copper sulfides. And that's where they're getting their energy. And of course, that's liberating the copper. And copper can be very toxic. So there's either an actinobacteria filamentous guy there or a fungus there that is benefiting from this energy-producing mechanism of the bacteria, and the fungi or the actinobacteria are taking care of the toxic copper by storing it in their hyphae. Okay? So these are pretty cool bugs, and we're beginning to write that up. And I have to tell you, these guys take a long time to grow in culture. So we've been working on these guys for 10 years. They take about 2.5 years to even show up in culture, and then they take many years more to do this chemistry. So it's not like medical microbiology. You get your answer the next day. So that's the background, okay? So we've been studying these with a lot of techniques, and one of the techniques that we often start with and end with and frequently revisit is visualization, because we are a visual species, right? We're an eye-minded species, and so I got to see what they look like. So we look at them in microspace with scanning electron microscopy and electron microprobes. And we took out some samples about a year ago that we had prepared very early on in the history of this project. And I was looking where on the samples, because these are little tiny samples that we store, where on the sample we wanted to re-examine so we could produce maybe some new images as we're preparing to publish later this year. And I look, and it's fuzzy and brown. And I thought, well, that's odd. And I had my colleagues look, and they're like, it's fuzzy and brown, okay? So our clue that these guys were living on this material to begin with was it was fuzzy and brown. And Carl Francis, who's the curator of the Harvard Mineral Museum, actually started this project by complaining to me that his copper sulfide samples in the Harvard Mineral Museum were getting cruddy, and what should he do about it? And he said, do you think it's life? And I said, I don't know, but that would be cool. And so that's what got it started. So the brown fuzz, and I'm thinking, wait a minute, we have air dried them, vacuum dried them, at 120 degrees. We have precipitated gold, palladium on them so that they're electron dense so that we can see them. We put them in there like a zillion times and zapped them with the electron beams. And these little suckers are growing back up through the gold palladium coating. Now, I say that that's an extremophile that is going somewhere, and we better watch that we don't take those kinds of bugs along with us on spacecraft. So I just use that to illustrate that there's not much water in that environment. We've done all this nasty stuff to these little guys, and they're still like, we don't care for you. We're just growing back up through the specimen stub. So the idea that life is tough, man, it's really tough. And so those kinds of pieces of information, I think, are giving me hope that what we see in the extremophile world, we can take pieces of those capabilities and infer what might be surviving there in terms of basic processes when we look at habitability, like someone like Pan is trying to map out on Mars, and to match these capabilities up on a fundamental level.
And here's, to my mind, where things get extraordinarily cool. I mean, all of this is cool, but I remember talking to a variety of very well-known people about this, and they said, okay, microbes, you find a microbe on Mars, to most people it's like not necessarily a big deal. It's, we don't even necessarily know that it didn't come from Earth and all this. But if we are able to determine that it's a microbe that had a different genesis than life on Earth, then what you have is not just life 101 here on Earth, but you have two genesis in one kind of chump change solar system, which means that the likelihood of there being widespread life goes up like that. So if we find one of those little things, or if they are found or identified or they were once there, then there are huge implications to that. Chris, I see that we're kind of running a little bit late. As you could tell, the panelists could all go on. We could talk for hours. What should we do in terms of taking questions? Or?
We can take a few questions. We started a little bit late, so why don't we take a few questions?
Okay, but before we do that, let me just ask Lisa a little bit about MAVEN, which is also a significant part of the picture here in terms of what's going to be happening. That's where there's actual funding and we know what's going to happen.
Actual funding. We like the actual kind of funding. MAVEN's next up after MSL. In 2 years, November 18th, 2013, the window opens. And MAVEN is a bit of an obscure science that's called aeronomy, which, by the way, the scientists who do that are called aeronomers. I learned this when we were doing the competition. And but it really is the physics of the upper atmosphere, as opposed to the atmospheric composition like the trace gas mission. And it is looking into what Pan was describing in terms of the atmosphere having been lost. And the primary theory is that if the dynamo were there and it stopped and there was no longer a magnetosphere at Mars and the atmosphere was ripped away by solar effects, MAVEN is going to look at atmospheric loss, what's there now, how it's leaving, how it's changing over the course of an Earth year, and then also measure the solar functions and all the solar energy and wind, and try to correlate between what's leaving and what's happening, and draw some conclusions about what is taking Mars' atmosphere now, as well as to extrapolate back and what we know about the early sun in the solar system back in the 4 billion, 3 billion years ago, and try to understand what Mars' atmosphere might have been like in the past, as well as understand between extrapolating into the past and understanding what's happening now is looking at the composition in a way that helps us understand. I mean, if you have carbon dioxide atmosphere and it's thick and it no longer is, it's got to have gone one of two places, down or up. And so MAVEN's going to look at that up piece of what's leaving. And if Pan also is on one of the instruments, are you on NCAMS as well?
No, it's being built in our group.
In the same
but-
lab. There's a very prolific lab at Goddard that produces instruments that look at the ions and neutrals. And if you wanted to add anything more detail about the science of MAVEN,
It's just extremely important when you have a system to think of a planet as a system, to understand what's in the hard stuff and what's in the volatile stuff. Volatile being either liquid or gas. And so because the planet lives in a dynamic environment, everything in the solar system, everything in the universe is dynamic to some extent. The dynamics determine what you have and in what kind of condition you have it. So it's an extremely important mission because we need to understand the context of what we learn on the surface in the context of what's going on above the surface and how far the footprint of the planet goes beyond the hard parts. And I might add one other thing about MAVEN and every other orbital mission. For ET to phone home and give us the data that we get on the surface, we need these orbital assets to relay that data. And if you don't have them and you have to go direct to Earth, you can only send back a little bit of stuff. There's hardly any bandwidth. You can hardly ever do it. And you can't maximize the time on the planet. So aside from the intrinsically very important science that you get orbitally, you also need that cell phone network.
and that's part of Mars as a program, is we do require every orbiter to carry that kind of relay equipment for that reason. So that's, sort of the program aspect of it.
And I hate to do this, but if I could just jump in. Deborah, if you could just tell us a little bit about 16 and 18 in terms of what the science of that would be.
So we've put together two missions, 16 and 18, and they are currently in cooperation with ESA, European Space Agency. They are part of the European program that they're calling ExploreMars. And so there's an orbiter in 2016, which is called the Trace Gas Orbiter. And then the other part that the Europeans are contributing to is the 2018 Joint Mars Rover mission. Now, the 2018 mission is the mission that would be selecting and caching samples on the surface of Mars, which would be potentially brought back to Earth at a later date, as Lisa mentioned. But to quickly just circle back to 2016, the Europeans are providing the spacecraft, and the U.S. contribution is the science instruments that ride on that spacecraft. Those instruments have been selected, and that mission is designed to look at a number of gases in the atmosphere that have very, very small contributions to the total atmosphere of Mars, of which there isn't that much in the first place. So these are very, very, very tiny little parts. But the intent of them is to look for these very, very small species, one of which is methane, which we know on Earth is a byproduct of biological organisms. It's possible as well that methane, we also know on Earth that methane can be produced by abiotic sources, volcanoes, for example. So we don't know what we're going to find or what the source of this methane might be on Mars, but we're following up on a discovery that was made to try to understand whether this methane exists and why is it there. I think I'll keep it short since we're out of time.
I want to add one comment to that, and then it will be a very short comment. And one is that the 18 rover is also being designed to satisfy astrobiology, and to do in situ astrobiology. The science of 18 is not just packing the bags for the return trip home. It has intrinsic science value of doing subsurface sampling with the European drill and looking for organics in those as well. And the other thing is for those of you who heard the talks about the decadal survey yesterday or who have read it, when they talked about, maybe it was this morning, the days have run together, talked about having to constrain the caching mission that was presented to the decadal. This is how we do it. We work with partners. The Europeans have 850 million euro into this program. And that's one of the ways we constrain the U.S. cost of this. And the other is by looking at it and looking at, instead of 2 rovers or whatever we could send, putting them together and merging our science objectives to the interest of both partners. And that's an important thing going forward with international collaborations, being able to look at the problem in one way and put it back together again in a way that meets constraints. Science enabling.
I know we've put a huge amount on the table here. Questions?
Mars Reconnaissance Orbiter seems to be discovering a lot of huge buried glaciers of water ice in various points on the planet, and this to me is insanely fascinating. Can all of you, or who, anyway, talk about how extensive are these glaciers? How important might they be for Mars science generally, Mars life science in particular, and their suitability for possible destinations for human inhabitants?
I'm going to leave the human piece for someone else because that's not my area. But what I can say is that it's very clear that water ice persists beneath the surface of Mars far greater than we had ever imagined in the past.
Well, I mean, the implications for life would be very significant if somewhere there was a sweet spot where at least the ice could transiently be liquid water. And that might be at an intersection in the subsurface, which is what I'm hoping for, where you would get heating from the interior of the planet. We don't understand and have not measured well the geothermal gradient in Mars yet, but that's certainly on the list of things we need to do. And we imagine that there's maybe an intersection where the ice layer intersects that amount of heat where you might get liquid water, and that would be a sweet spot to look for.
It's also well known now that Antarctica, for instance, is a huge ecosystem. I mean, there's microbial life going down miles in the ice.
Yeah.
And that's something that is a relatively new understanding and could have implications there.
Hi, I'm Mary Liscombe from the Krista McAuliffe Center at Framingham State University. And Penny, I think my question might be mostly for you. And are you concerned at all about contamination going to Mars, not only what you bring there and what you bring back, but also, I guess I'm wondering about, I'm not clear totally about the SpaceX agendas, except they seem to want to get there first, and could that be a contamination issue for you? And do they have science missions that you coordinate with, or is this more of a race in space for them?
I serve on NASA's Planetary Protection Subcommittee and have for a number of years, and I have always been concerned about this issue. So there's a multi-part answer. I'll try to do it fast. One is that I think that the work that we do in our extremophile environments, where we're often going into subsurface environments where no human has ever gone, is a model. It's an excellent model for how we try to constrain or control the impact that we have on the system that we're studying. So there are ways to try to work on that on Earth, and I and others are working on that issue. It's a very great concern. And in fact, unfortunately, Cassie Conley, who was on one of the panels yesterday morning as the Planetary Protection Officer, was not able to be here today. She had to go to JPL. But one of the things that we worry about a great deal on the panel, of course, is the whole issue of nationally advanced space missions and how planetary protection folds into this, but also of great concern to us and on our radar now, both within our subcommittee and internationally within COSPAR and the groups within COSPAR that worry about planetary protection, is how do we raise the consciousness, I guess, of the people who are interested in commercial space in adhering to these, what we think are scientifically and in fact ethically critical guidelines for not screwing up another planet. There are practical reasons for being extremely concerned about this, and there are also, in my view, ethical reasons. You know, if there are indeed life forms on another planet, then that's their planet, and they're the life form that you know, is indigenous to that environment, and as conscious beings, it's really in our purview to protect that at all costs. So this is a very politically, ethically, and scientifically sensitive area, and so we are worrying a great deal, and feelers are, you know, being put out to people in the commercial space arena who have aspirations to land on another planetary body, particularly Mars.
I'm going to add something to that, and that is that the notion of planetary protection and how you prepare and mitigate potential biological contamination is one part of it. The second part of it, if you're going to actually look for life or complicated chemistry, is something called forward organic contamination. Because typically the way we get rid of bugs is we heat to a certain level, which is good enough to kill the bugs, but not to get rid of the chemical carcasses of the bugs. So in that regard, we've developed protocols which are very difficult to execute for doing organic cleanliness, and then other protocols for truthing that when you get to the other planet. What's become apparent, and this is where you bring in all of science and technology, is that we are now at the limit where our requirements for organic cleanliness are so close to the limit of our ability to verify that cleanliness that we almost can't do it. Once we get to sub-parts per billion, or a few parts per billion, or a certain distribution per square centimeter, it becomes very, very tough. So this is an area where everyone can contribute, and those of us who support commercialization of space exploration, we should all be contributing to that discussion.
Yeah.
I'm afraid we have two more questions. I'm sorry.
Okay. Hi, I'm Elizabeth Wallace. When I came to this conference, I actually wasn't interested in Mars at all. No offense. Please don't take offense. But I have since been able to connect it to me by listening to everybody. And I was at the Astronomical Society of the Pacific meeting, and Dr. Waleed Abdul-Latif was one of the speakers, and he talked about the importance of storytelling in getting your message across. And storytelling is not just verbal, and it is verbal. It's also visual. When a storyteller tells oral narrative, they're picturing the story. They're not memorizing something. It's using words, obviously. It's using logic and math, because you have to have a logical outcome to the story. It has to be based on something. You use nature in all of it. You use your body to express it, and if you were standing up telling the story about being in the cave, you probably would be doing multiple things because you come from a kinesthetic background of dance. And it's also personal and interpersonal. I think the interpersonal is somewhat missing from the communication to the public. And the way I was able, if I was going to bring the information back from this conference to kids that I work with, I would say, you know, once I went on a mission, and it was an interpersonal mission to find out something about myself. And I launched from the BWI airport, and the only place that this plane would go was to New Mexico. I wanted to, and it would, I mean, sorry, the only place it would land would be Albuquerque. And I had to start my exploration from there. And when I looked at the ground looked like that Mars picture. When I first saw that Mars picture when I was a kid, I was not interested in Mars. There's nothing there. When I looked at New Mexico for the first time, how can anybody live here? There's no water. And then I found that other missions had gone before me. Whole Foods was there. There were supplies. And I sat in front of... I sat on a bench outside Whole Foods and looked at the Sandia Mountains and saw how beautiful this place was. And I decided to stay longer. And then I went and started to discover things that I never would have discovered before. And the second time I took a mission there, I took another human with me, my daughter. And I have gone 5 times because one mission to New Mexico is not enough. So I just wanted to say that probably if Dr. Boston hadn't been here, I might not have made that connection. I might not have been thinking about New Mexico through this whole thing. But New Mexico, to me, as to many people who've ever been there, is the land of enchantment. And now, possibly, I can see Mars as also a land of enchantment. Thank you.
Cool. Thank you.
The question. How much do you see the arts, storytelling, to be incorporated with the way scientists release their data, promote their data, and try to involve the community? How do you see that? Perhaps Ms. Boston can.
Well, I am saturated with art, and I talk all the time, obviously. So I love storytelling. I think of everything I do in teaching. You know, I have a pretty heavy teaching load, and so I'm talking like all the time. And so my teaching is sort of my daily exposure to storytelling, but every time I give a public talk, which is like a lot, it's all storytelling. And in fact, science itself, what I tell my graduate students is they're learning the difficult and very often dry and prosaic art of putting together either their dissertation or their first proposal for funding, is that even though this is formal science writing, it needs to have all of the components of a story. It needs to have a narrative. It needs to have development. It needs to have characters, which in this case are the science. And so really the human psyche is so oriented towards the story as we understand it that I think it's a natural way of communication.
Okay. Lisa, did you want to?
Well, I just want to say one of the other features of the Mars program is we actually have an education program that, Michelle Viati, who was a moderator yesterday and didn't do a lot of her own speaking, she coordinates and manages that for us. And it enables us to pull together the amazing, not just the stories, but the information and disseminate it back out to the community in all kinds of venues and age-appropriate ways, and to make connections between the various science that perhaps if we didn't have a single clearinghouse for that, it's not a clearinghouse. I mean, people generate their own material, but someone paying attention to it in a coherent way, we might not have as robust an education program as we do coming from the Mars program.
And
Thank you.
Just a brief FYI, the book that I wrote is very much a narrative. It's directly for a general audience, and it was taking that same idea that what the science is a series of narratives, and to try to tell the story of the science through many of the scientists. Yes.
Hello, I'm Karina Chung. I'm a grad student in geophysics at Virginia Tech. My project's actually looking at the crust of Mars. Given that it's more geophysics, I've never really been, that interested in biology, but recently, colleagues and the geobiology division in our department would talk about, evolution of life. And at the beginning of the year, I came across a science article about arsenic-based life. I don't know if you guys heard of that. I thought that was really fascinating because, for our life forms, arsenic is basically our poison. So for them to be not carbon-based, but more arsenic-based, I was wondering.
That's not correct.
Let me
It's not-
address
okay.
that. The work that was presented in Science is not about arsenic-based life. No one has made any assertion of arsenic-based life. The woman who published the paper said that there was some life that she had studied that appeared to be able to not die if it incorporated arsenate, arsenic with oxygen, in place of another anion, phosphate. So while it's somewhat controversial, it's real important to know that the life is carbon-based, not arsenic-based.
Okay, good to know. So the question is, since we were on the topic of extremophiles, are there missions in the future for Mars missions, like in situ measurements, that we will still look for life forms near water, or will we be going to more extreme places to look for life?
There are a lot of considerations in answering that question. There's the practical consideration, which is, although we're landing larger and larger things with more incredible landing systems, we still have some limitations. So everywhere we land has to be safe from an engineering and practical landing point of view. And then they have to be able to operate. So Phoenix operated for a few months because of the winter approaching, and there was no solar power for it. So there's some practical considerations with where we land, and there are also planetary protection considerations with where we land. If we go drilling into ice, the potential, or drilling into somewhere where there's water, the potential for contamination, one way or another, is increased dramatically. And I'm sure Penny can talk to special regions better than I can. If we had time, we could have a long conversation about it. But so the considerations of going to these special regions or areas with the water first, or soon, we have to go and get through and understand the planet more, and then look at going to places that are harder to implement missions without violating our treaties and our commitment to not contaminating another planet.
Do we have time? One quick question and one quick answer.
I'm a grad student at Michigan right now, and I'm actually on the Maven team, so I'm looking forward to talking to you.
Yay.
Yeah.
There's
but,
several of us here. We
I
can
know.
have we
I'm
can
really
have lunch.
excited. But one of the big things, right, around 10 years ago, crustal magnetic fields were found on Mars, which is a really exciting finding. And since Maven will have a magnetometer, it would be really nice to look at the correlation between atmospheric loss and the magnetic fields. And so I was just wondering if between the rovers and the satellites, what you guys thought, if there's any emphasis on looking at how the crustal fields influence just water in general and where it's gone, and if you guys feel like that's been, at the high level, if that's something that's interesting, because on the science, lower level it is, but it's hard to tell at headquarters and all things.
I'll try that one. So there's magnetism and there's magnetism. There's remnant magnetism in rocks that are accessible that tell you something about the local environment, and there's also things that you can learn about the whole planet environment. So the question of whether or not that has relevance for the chemistry that takes place or the redox potential of the area, it's certainly all related. The electrical environment, the physical environment from the interior going on out is very important to enabling the chemistry. However, it's also very difficult to tell whether you're looking at the remnants of whole planet magnetic field or something that's regional. So certainly that's something that's worth asking a lot of questions about, and there have been proposals before to put other types of magnetometers in place. There are small proposals, I know of at least one from JPL that I think is in a phase A study, Bruce Bannert stuff, which is a geophysics type mission for which people have asserted that understanding the geophysics of the rocks and the electrical and magnetic environment would be key to understanding the crustal behavior and trying to figure out the relative dynamics of the crust to the dynamics of the interior, the deeper interior, and what that portends for the maintenance of liquid water and other chemical reservoirs. Does that help?
Yeah, I'm sorry, but did you say that they get funded then, or?
Yeah,
It's in a
phase A.
competitive phase A. There are 3 proposals that will be submitting their concept study reports next year.
I think another point that perhaps this might be helpful to you as a graduate student is to definitely take a look at the decadal survey and the priorities that the decadal survey put out, but also as a Mars scientist, or take a look at the MEPAG, Mars Exploration Program Analysis Group's goals and objectives document, okay? Because that outlines the highest priorities that the Mars community of scientists has agreed upon, and also so the priority of goals, and there's a whole lot of sub-goals in there, and magnetism of a planet is one of those, but it'll help you sort of understand why the priorities for the program are laid out the way they are. They're in response to this MEPAG document, and you can find that on the MEPAG website.
Thank you all. We regret that we're kind of late, but as you can tell, there's a great deal of excitement, and we could talk for hours.